talking about the M5-instantons in NPO.
All right, for any of the organizers that are in the audience, thank you for organizing this wonderful conference. This is my first time in Cambridge, and it's very nice to be here. Today I'm going to tell you about the moduli dependence of instantons in F-theory, and in a 15-minute talk, there's only so much that I can say, so I'm going to focus on some illustrative examples and then make some concluding remarks afterwards, some generalizations. This is based on some work from last summer with Miriam and Iñaki Garcia Echevarria, both of whom are in the audience, and also based on two projects that are currently ongoing and are being drafted, but we're still drawing some conclusions. With Miriam, with Ron Donaghy, with Joe Marsano, and then another project with Miriam and Thomas Grimm and Dennis Clavers. Most of the things I say in this talk are going to be on the first two collaborations here, but the third one has heavily influenced my thinking as well. So the motivation for instantons in F-theory, we have heard many talks on the relevance of instantons so far in this conference, and the biggest thing is that they can generate superpotential corrections. So in particular, the structure of the superpotential correction takes this heuristic form where you have a divisor D in an elliptically fibered Calabi-Yau fourfold and an associated Kähler modulus, and you have this prefactor here A, and this is what I'm going to spend most of my time talking about. So the prefactor depends on the complex structure moduli and the D3 brane moduli, and maybe some others as well that I won't talk about. But a priori, essentially the same motivations in F-theory hold for studying instantons as the motivations in 2B for studying Euclidean D3s. And those are, first and foremost, moduli stabilization. The two best known moduli stabilization scenarios use these in very important ways to stabilize some of their Kähler moduli. And in particular, one of the things that is often that is sort of discarded is this, the moduli dependence of this A in these scenarios. And the basic reason is that you have complex structure stabilized at some high scale based on some choices that you've made about fluxes. And so you can evaluate A on the vacuum locus in complex structure moduli. But we're going to actually talk about the moduli dependence. The other reason why you might want to study instantons in F-theory is that we know from the type 2 case that you can non-perturbatively generate couplings involving charged matter fields which are forbidden under anomalous U1 symmetries. These were a couple of papers from 2006 that started off an instanton mini revolution for the couple of years afterwards. So the essential questions that I would like to address is, in the known examples, this prefactor A has some sort of miraculous structure that you will see explicitly, and whenever we see something that turns out to look very nice in a computation, we might ask, why is this happening and what is the physics that governs it? So that's one of the things I'll focus on in a couple of examples. And all of the explicit computations that are known in the literature to date are in heterotic models where you consider Pfaffian prefactors of heterotic worldsheet instantons computed as a function of vector bundle moduli. And so you might want to also ask the question, how does one understand or compute the Pfaffian in F-theory? If I use the word Pfaffian, I effectively mean this prefactor A here, and I'll compute it by looking at certain fermionic zero modes. So there has been a good bit of previous work on M5-instantons. There were a number of seminal works in the 90s by these people, and in 2009 and 2010, there have been, starting with this paper, a very nice paper by some people who are in the audience. There were all of these other papers that followed it up, saying various things about instantons and F-theory, and my thoughts on this have been heavily influenced by all of these. So the outline of my talk is that I would like to review some of the basic aspects of instantons and duality. After addressing some of those issues, I'd like to learn some of the lessons you learned from heterotic duality about instantons and F-theory. Moving from there, I'd like to focus on some examples. I'd like to show you some examples of this prefactor, and that it has some beautiful substructure that could potentially be relevant for physics depending on what global compactification you're considering. And one of those things that we'll see as advertised in Kumran's talk is that points of E8 enhancement have some interesting physics associated with them corresponding to the instanton corrections. And then at the end, I'll conjecture for how you might compute in F-theory models without a heterotic dual this prefactor in a way very analogous to how one would compute it in the heterotic string. So the lightning review that I would like to remind you of is that the structure of superpotential corrections due to instantons depends heavily on the structure of fermionic zero modes. So in particular, one of the types of zero modes that is very crucial in type 2B is charged 3-7 modes, If they're present and there are certain couplings in the instanton action, if those couplings are of a suitable form, the prefactor can include fields that are chiral matter fields charged under G4D. And this is very important in type 2 because, for example, Majorana neutrino masses are always forbidden. The 10-10-5 Yukawa coupling in SU5 guts that gives the top quark its mass is always forbidden. And I'm not going to address these issues here. I think Timo might have a little bit to say about this in his talk tomorrow, so I'll refer you to him. On the other hand, if the charge modes are absent, this moduli-dependent prefactor doesn't have any matter fields in it. But the basic idea is that as you move in what I'll, for the time being, call the gauge moduli space, as you move around, at certain codimension 1 loci, you can get extra zero modes, fermionic zero modes, that will cause the prefactor to vanish. And that's associated with a jump in the number of zero modes, much like the associated jumps that Laura was talking about in her talk in a different computation in the heterotic string. So when I say gauge moduli, here is, what I mean is D7 brane moduli in type 2b, bundle moduli in the heterotic string, and complex structure moduli in F-theory. One of the things that has been prevalent the last couple of years is thinking about F-theory from all three of these points of view. And these are the moduli that typically appear in these prefactors. So I don't think I need to motivate that the structure of any moduli dependence in this prefactor is clearly going to be relevant for physics through the effects of the scalar potential. So the instanton duality that I'd briefly like to describe is between the heterotic string on the left side, where you have a heterotic world sheet instanton wrapping a curve sigma. I will use the term sigma throughout in a base B2. You have a holomorphic vector bundle specified in the spectral cover formalism, and this corresponds to specifying a curve eta. That is one of the things that determines the moduli in C. And on the F-theory side, you have a Calabi-Yau fourfold with some G4 flux. One of the key features when you have a heterotic dual is that the base of the elliptically fibered Calabi-Yau fourfold B3 is itself a P1 fibration over B2, which is the heterotic base. So the picture that you should have in your mind here is that in all of these setups, this curve sigma plays a key role. And sigma is the curve for the world sheet instanton in the heterotic string, and its inverse images in F-theory under various fibrations is how you would view it as a Euclidean D3 or an M5. So the fermionic left movers in the heterotic string are the ones that are relevant for talking about zeros, and you can compute them as a function of moduli space via computing this line bundle cohomology in the spectral cover formalism. Simply, it's the restriction of the vector bundle to the instanton curve tensored by O of -1. You can really get your hands on this thing. From the point of view of type 2, these things have a natural interpretation as the fermionic 3-7 strings because this curve sigma actually is where the gut stack intersects the instanton. And also, there's a story that I won't say too much about today from the point of view of the M5 effective action and theta divisors on the intermediate Jacobian of the M5. So the point is that in the heterotic string, what you would do is that this prefactor vanishes when the cohomology becomes non-trivial. And so you would compute explicitly the prefactor by studying maps in the long exact sequence in cohomology associated with this sheaf cohomology group. So, but the point is that under duality, this is the Euclidean D3 or M5 instanton prefactor. So the structure of the prefactor takes a particular form usually, which is sort of the first sign that it is somewhat miraculous. This prefactor takes the form of some polynomials raised to some powers ki. And so when you compute these things, it's a very satisfying thing to have your code spit out some very long polynomial, and then you hit factor, and it simplifies greatly. So one of the questions that you might ask is, what is the physical content associated with each one of these polynomials fi? And I should point out, because it's relevant for discussions of the scalar potential, that in these cases, in all of the known examples I've seen, k is typically greater than 1. So that is an important thing. So some of the lessons that we learned in the paper from last year from heterotic duality, first and foremost, is that the prefactors only depend on a subset of the moduli, and it's those moduli that determine the 3-7 intersections. So the way that you should think about this is you have some prefactor that is moduli dependent. As you vary those moduli, the 7 branes are moving around in the instanton world volume. And as that happens, sometimes you will get additional zero modes, and it can zero out and cause a prefactor 0. So the point is that since these depend on a local subset of the full moduli data, namely that in the heterotic string which restricts to the instanton curve, the same correction could arise in many compactifications because it's not the full moduli data of the heterotic string compactification. So given that background, you might ask, what might these prefactors look like in explicitly computed examples? So I should say that the two examples that I'll discuss today, we have some other examples, but I understand the most about these. These were originally computed in a heterotic compactification by Bookbinder, Donaghy, and Overett. They have very nice structure, and Gottfried Curio, in a series of papers from 2008 to 2010, wanted to ask what is governing the structure of these things. And then we have followed up and broadened that a little bit and also made some F-theory statements. So the
5 minutes.
Oh, 5 minutes, okay. So the compactification data is given here, and since I only have 5 minutes, maybe I'll skip right to the example. You can see that the prefactor computed here is a function of these alphas, betas, and gammas. So these are the things that appear in the spectral curve equation above the curve sigma that governs the 7 brane intersections with the instanton. So these explicitly are the ones that govern the structure of the singularity enhancement in the instanton world volume. So a particular thing to note here is if you ask what is the significance of this polynomial f sub lambda that appears here, raised to the 4th power, what is the significance of this polynomial itself? It turns out that f sub lambda is equal to 0 if and only if another particular line bundle gets a section. So sections of the line bundle up here, which is the line bundle you compute for the Pfaffian, is related to this other line bundle down here. And this is a somewhat generic phenomenon. So you can understand this via decomposition. And one comment that I would mention is that this line bundle here, that is the relevant one, is the one that you compute the square of in the heterotic string that is like the G4 wedge G4 part in the D3 brane tadpole contribution in F-theory. So in example 2, this is the compactification data. It's similar, but some of the details are different. We still have a spectral curve over the instanton, and we have moduli appearing in it that governs the 7 brane intersections with the instanton. And in this particular case, it factorizes again, and we see this, and we have this polynomial f sub e8 to the 4th. And in particular, one thing that you might notice is that the moduli of phi type and chi type show up, but not the moduli of psi type. And that is going to be very important. So it turns out that this fe8 to the 4th here, this fe8 polynomial is precisely the determinant of this matrix. This matrix, it turns out, is the resultant of A2 and A3. And effectively what that means from the point of view of the F-theory physics is that the superpotential vanishes if and only if there's a point of E8 in the instanton world volume. Notice that in this case, it's codimension 1 in the moduli space. There's only one polynomial that you have to set to 0. That is special. But this is something that was very interesting to us because we knew it was important in the phenomenology, in the string phenomenology literature too. So just to remind you of what the setup is we have an instanton wrapping a divisor here. Apologies for my terrible artistic skills. We have S gut here, and they're intersecting at this blue curve. And the point is that generically, we have gauge symmetry E6 in 4 dimensions. And so we'll generically have this being an E6 curve here, where the gut stack intersects the instanton. And generically, for generic moduli, the superpotential is non-zero. But then if you tune the moduli such that you get not a single point, one point is enough, but you could have more points of E8 enhancement, then it turns out that the superpotential is 0. And in this example, this is if and only if. So we were told during Kumran's talk that points of E8 give a natural flavor structure, can give rise to minimal gauge mediation, and can give rise to an interesting PMNS matrix. So one of the things that when that paper came out, some friends and I were talking about, and one thing he mentioned in his talk, is that why would we be at such a high codimension locus in the complex structure moduli space? So this is not in any way a criticism of that, because you could ask this about any SU5 gut in general. Given that the SU5 locus is typically high codimension in the moduli space of an elliptically fibered Calabi fourfold, why would moduli stabilization fix us there? So you would like to have some reason from the point of view of the superpotential or the Kähler potential to believe that these points are special. So a question that you might ask is the connection between E8 points and superpotential zeros just a fluke, or is it more general? In particular, does it appear in SU5 cases? So the point is, and since I'm running low on time, I'll just state the result. When you have a point of E8 in the instanton world volume, something very special happens in the geometry. And in the presence of E8 points, this bundle gets a section. But in the same way that we saw that sort of sub-bundles of the bundle you compute to compute the Pfaffian can matter in determining the structure of the Pfaffian, we see that here. So in particular, if you were to factorize the Pfaffian line bundle off like this into this guy and this factor, you know that in the presence of LE8 points, this thing is getting a section, and so then you can table the question of whether or not this gets a section and you have a superpotential 0 into this bundle. And you can set conditions and ask the question, when will L points of E8 cause a superpotential 0 for an E6 or an SU5 gut? And this was a computation we did, and here is the result. And a nice thing to state is that it checks in the known examples, and moreover, that when there's a notion of maximal number of E8 points as well, and when that happens, the superpotential will vanish. So we have these conditions here. We have a conjecture for how to compute these in F-theory without a heterotic tool, but since I'm out of time, I will not say much about it. And we have some reasons to believe that that is true as well from the heterotic point of view, from the type 2B point of view, and also from the M-theory point of view. So concluding, the moduli-dependent instanton prefactors have a rich structure that's important for physics. Typically, they factorize into non-trivial powers of beautiful polynomials. And in every case we've seen, each polynomial has some deeper understanding that could be relevant for physics. One of the things that we saw is that you could decompose it into, you could decompose their dependence into other line bundles, including this one that is related to E8. So, and moreover, these points of E8 enhancement can cause superpotential zeros even for SU5 guts. So since I didn't tell you much about the conjecture, I'll leave it there. Just tell you that we're trying to make sense of this in type 2B and in heterotic and possibly in M-theory. So thank you very much.
Questions? Yes.
So how about the kinetic term? So usually the superpotential is a section of a bundle. Mm-hmm. So if you don't know which bundle we have chosen, you wouldn't know what the 0 means. Is it clear what the kinetic terms are? The D terms, in other words. That will determine whether there's actual 0 or not in the dW squared.
It vanishes to a higher order, for sure.
Higher order.
Yeah. Typically, the vanishing is to a higher order. Remember that I told you that generically this will factor. These polynomials that show up in the Pfaffian take the form f to the I, k to the I, and k to the I is typically greater than 1. So the superpotential will 0, but also derivatives evaluated along the vanishing locus of the superpotential.
No, dW I know. I'm talking about norm with e to the k factor. In other words, the D term will determine whether or not whether you're in good coordinates or not. In other words, you're choosing a coordinate to describe this complex moduli. If you're in bad coordinates, so to speak, you can get zeros. That's what I'm saying. In other words, if you just W is a section of a bundle, so if you just rescale it by a factor of z to the I, you cannot introduce artificial zeros. Of course, I don't think yours is artificial. I just want to ask the question. So, if you do not know what the D term is, you wouldn't know what the meaning of the 0 is.
I haven't thought about that issue, but I believe that these are real zeros. Yeah.
Is there an actual point of unbroken E8 on the heterotic side of these zeros?
Not point of E8 generically, you mean?
So, I mean, you said that at these zeros, you have an E8 enhancement on the F-theory side.
Right.
So I'm just wondering, is there a way to think about where that E8 comes from on the heterotic side?
That's right. So if you have a rank 3 bundle, and so you have moduli showing up in sections A0, A2, and A3. And so this example that I showed you is sort of when all of the A2 through AN have a common 0 on this curve sigma.
So you're really modifying the spectral cover at this point?
That's right. You're modifying the spectral cover at this point, and it's sort of enhancing all the way up to E8.
One last question.
Can you explain the part about when you don't have a heterotic dual?
Yeah, so trying to say something. Yeah, apologies for trying to bite off a little more than I can chew here. Yeah, so this project is also with Joe, and one of the things that definitely affects our thinking here is the fact that when you do have a heterotic dual, you have this nice cylinder structure that is interpolating between the heterotic side and the F-theory side. So the conjecture is that effectively the spectral curve, when you intersect your spectral divisor with the gut stack, the spectral curve that you get covering the sigma in the instanton world volume, and it's not the spectral cover, it's a spectral curve because you've intersected with the instanton world volume, that there's a line bundle cohomology that you could compute there, and moreover, it's isomorphic to the heterotic cohomology when a dual exists. But in the spirit of the work that you guys are doing, this is the analogous thing that you would compute when a dual does not exist. The thing that's nice about it, and the non-trivial checks, so it is isomorphic when a dual exists, but in type 2B, this is the spectral curve over the 3-7 intersection mode, over the 3-7 intersection. So this very much has the flavor of these lambda modes.
And we have some statements about M theory, but we're also working that out. So.
Okay, I think we should close this part of the session. Thank you.